Hello, everyone. Welcome to the second part of the Towards Marine Autonomy session. We'll start our session with Professor Boon. He's a professor of electrical and computer engineering at KAUST. His field of research is on photoelectronics and photonics. The title of his talk will be about optical wireless communication for underwater Internet of Things. So please join me in welcoming Professor Boon.
Thank you all. I know that this is the last sessions, and I just told Thank that his invitation is not too sincere because usually all those not too important speaker they'll put into the last session, and I'll try to make it short. So instead of talking about half an hour, I try to finish everything in 20 minutes, so that I can then finish the entire sessions earlier and have fun. All right, what I'm going to talk about, I'm not a control engineering, so I do not know anything about equation and do not know anything about control. What I'm talking about is something that we are working in the lab and trying to build some devices module as well as the optical communications and deploy in the sea so that we'll be able to have very high bandwidth of communications between two sensors, for example, ROV. We know all of those things. Thanks, Ibrahima. And many other speakers give very good introductions. Why underwater, why deploying the optical communications or bring internet to underwater is important. So I'll skip this part. And application-wise, I think in this community, we all know about how significant it is to be able to bring significant optical bandwidth to the underwater environment so that be able to control all the equipment, devices, and to perform activities that we are hoping for. And most of the activity, we still very much talk about the, in this kingdom, or at KAUST specifically, we don't talk about military application because we don't work on the space, but we very much focus our application case on the oil exploration, fishery, and other scientific research. And environmental research become quite important thing. Just now, Professor Sharma was talking about the coral reef and etc. And that is one of the key focus that we hope to be able to address as well. Our bigger vision and bigger goal would be linking all the layers of the communications together. We know that we have the satellite to ground communications. Now it's somewhat established. And we also know that in ground, we have many different forms of communications. Then to the seas as well, but undersea is still somewhat lack of because of the technology gap. And the ultimate goal in our lab is by using light-based communications to complement the wireless communications that we are using everywhere, so that be able to integrate all those different layers of communications together to achieve satellite, air, ground, oceans, and by using optical wireless comm. But today I'm going to focus mainly on the underwater. We Carlos Duty is a very respected climate scientist, my very good colleague and friends. We wrote a op-ed to challenge the community, particularly in the technical community, to understand our oceans a bit better, because we have no idea what is down there, say 3 or 4 kilometers below the surface, and still a lot of things that we do not know. So that is the op-ed that if you're interested, can take a look. And also another key objective, since he's the climate scientist, he always curious about and wanted to know more about sound. How and what is the effect of sound, especially man-made sound and human make noise, affecting the sea animal and sea mammal. So that's another motivations. We wanted to develop good technology that create a very silent ocean instead of still continue using the avionics, acoustic, or sound-based communications technique. I believe people see this before, and we know that until today, we still in underwater, we still use acoustic. Acoustic, the bandwidth, when we're talking about bandwidth, is how much data can we send and communicate within the ocean. That is still very much limited to a few tens of kilohertz bandwidth, that's 10 of kilobits per second. of the data rates, right? Essentially, if I'm an old man, so when in the first generations of internet, we always plug onto our telephone, and those are the speed that we are very much talking about. If you're talking about acoustic, although they'd be able to send very, very long distance, up to say a few tens of kilometers, but bit rate is an issue, and the data rate is the issue. And another way is the RF. RF is what we are using for our portable devices, right? Linked to the tower, the cell tower, so that we'll be able to get our cell phone power up. So that although being able to go up to several hundreds megabits per second, but that again, in underwater ambient, all the microwave will be absorbed in meters. So we cannot even send any meaningful, send to meaningful distance if you want to use RF. Therefore, the balance things to us is then be LED, that's light-based technology, or basic using laser. In LED, we still have some limitation because LED, you cannot turn it on and off. That we call as demodulation for too fast. We very much limit to a few tens of megabit per second, push it a little bit up to 100 megabit per second. But in our case, we always wanted to have gigabit per second. What does it mean by gigabit per second? Gigabit per second, essentially, we are very much talking about better than the current acoustic method by a few tens of thousand times. So that is the data rate that we are very much aiming for. But it does come with some limitation. Light, you only have 2 color lights, whereas blue color, that will be able to go into the pure water, and the green color light go into the have slightly lower loss. When talking about loss, we're very much talking about fundamental absorptions of water as well as the scattering of the particle within the water. So the shore, close to the shore, turbid water, we use green color, and the deeper part of the ocean, we use blue color. So that ideally, we hope to be able to reach up to about 100 meters or so. That will be the meaningful distance that we're talking about. A very, very quick overview. It's not new. By using laser, Cold War, everybody bragged about their own technology. US and Russia, they are competing with technology, saying that, well, those are theoretical paper. That's very, very early paper. They want to send a laser source from satellite or plane, and hopefully being able to communicate with the submarine under the water. And ideally, theoretically, it's possible. And when we're talking about some of this early work, this early work in light-based communication underwater always linked to the LED, because LED become available, tiny little visible LED become available in early 2000, become booming. Research-wise, we're very much talking about 1990 something. 1991 is the first report, right? And then commercially available, then grow into the early late 1990 to 2000. So it's that year, those are the year the devices become available, so that being able to see a couple of those activity going can trace back to year 2000, when people begin to use LED to communicate in a very harsh environment, especially in the thermal vent, and communicate with the ROV. Then until 2017 or so, they begin to go into laser. We're quite fortunate. This is the work, 2017 is the experimental work performed by Lincoln Lab. They're very much using the same technique that we are reporting back in 2015. 2 labs that they are truly outstanding. If we talk about the underwater comm, we have to mention them because they put in a lot of effort, a huge group to develop it. One is Lincoln Lab. I would not go through everything in detail, but they also evolved slowly by using LED, which is slow, into the laser technology, which is fast in the gigabit per second over the year. And another one is Woodhull. Woodhull actually have a bigger vision. What they are developing essentially is go into the so-called omnidirectional. Everything have to be able to, if you want to send a signal, you just have a laser light and then blast all over the space, so that you do not need to have alignment. Sorry, Ibrahima. You talk a lot about those things, but this is what they are doing. Maybe you can look into what they are doing and then modify your model accordingly, and there will be big hit. And then detector as well, they are very much talking about omnidirectional detector. So those are technology that they're putting a lot of efforts over the year to develop those technology and deploy it to the real environment. As in our case, we begin to work on underwater comm back in about 2014 or so. And the first paper that report is very, very short distance, 6 meters or so, and using the blue color laser, 450 nanometers, get to about 2.5 gigabit per second, and then begin to use different type of modulations, a high level of modulation in optical communication language to get it up to about 4.8 gigabit per second. And then we begin to see a lot of different group, especially in China group. So in China, they're very resourceful. Whenever have Chinese group work on the same field, you better jump out, because we only have 2 students working on this field and they have 20. So fighting together with them on the bit rate, there's simply no way that we'll be able to beat them. We make sure that we have the preliminary or earlier work done and then jump away from what they are doing. So you begin to see a lot of group, especially Zhejiang's group, put in about 20, 30 people working on under the same things using laser, narrow beam laser for high bit rate communications. And then we jump into a long distance, try to push the distance. The distance that we try to get in this case is actually in our KAUST canal, and we managed to get about 20 meters. So when the students send me this draft, I think that there's no sign, because to send a longer distance, to communicate in longer distance, what you need to do, our conclusion in this paper, is to use higher power laser. So that's basically elementary school kid would understand. So I thought there's no need to publish this work. It turns out to be quite a well-cited work. Maybe we should do some simple science, but not the equations that I cannot understand from this particular community. Then we begin to understand the optical link within this very, very high turbulence, high salinity, high temperature gradient, and tower ambient, and include bubble as well. So I understand to develop a statistical link for the entire communication channel and how to mitigate them. So that will happen in some of those papers. Then begin to send high definition video. We also begin to look into the non-line of sight by using tapping onto the photon scattering, and begin to work on how to get the signal across from the water, go up to the surface, so that we'll be able to eventually fly a drone to pick out the signal. There are a lot of missing components that we need to develop, because unlike the optical communications that people are using for our internet and underwater fiber optics connect, we do not have many things, especially a very high performance laser as a transmitter that you can modulate at very, very fast bit rates. So we make our own semiconductor laser. We make a very narrow bandwidth on very narrow line width laser, so that we'll be able to push the single laser up to 10 gigabit per second. We also make our own photodetector array, so that we'll be able to get a small little photodetector array that being able to give us up to, say, 10 gigabit per second. So that is our goal. The current technology for our 5G technology, we're very much talking about 1 gigabit or so, right? Gigabit per second type of technology that we're using. It being able to push beyond up to 10 or so, then we're basically, the device not only taking care of the underwater communication, we basically being able to have a solution, partial solution, will not be the full solution, for our next generations, that 6G communication. That is one of the goals that we are building it. We begin to work on quite a bit of try to address the same problem as Brahima, try to mitigate the positioning, align, acquisition, and tracking. So the very straightforward idea will be try to use a bigger detection surface and based on solar cell, so that we'll be able to have a larger field of view, so that we'll be able to detect signal without having a very, very accurate alignment. Although the bit rate in this case dropped quite significantly, but at least being able to establish the optical link by using such a big solar cell panel that is very, very low cost. We also begin to, as I mentioned earlier, begin to put the our transceiver below the water, 3 meters, a few meters below the water, and then fly a drone to pick out the signal. That works together with Jeff Sharma. So it turns out to be very exciting. So what does it mean? How significant is this? If we're being able to have multiple nodes, multiple sensors placed in underwater ambient, and if the signal be able to hop from one transceiver to one node to another, ideally, we do not need to have a ROV scanning through all those different pickup signal from every single sensor or probe. We should be able to have the signal hop from one to another and fly a drone over to pick up all the signal in one go. So that is the idea. And that is the things that I've just discussed with Sinkyu, and hopefully be able to demonstrate it very quickly. To expand the field of view is always of interest in free space optical communication and also the underwater comm. And in this case, we develop our own technique that is based on a optical fiber. You can imagine optical fiber as a wave optical wire. It guides light. And in this case, if we happen to have a scintillating fiber, it means that be able to have those, put it up as a curtain, one light strike onto the surface of the scintillating fiber, the light will be converted into different color light and then guided it to a very small photodetector so that be able to have the very high bit rate, yet being able to have a very large detection surface. So that is the goal of the entire work. And of course, we also make the so-called fiber bundle and then tape it down to a small area for high-speed detections. Well, if you want to have high speed, we all know from our undergraduate that we need to reduce the RC time constant. To reduce it, you definitely have to have a very small aperture size for our photodetector, right? And you cannot have big photodetector and yet being able to get to a very large bandwidth of gigabit per gigahertz or so. So that is why we are doing so. By guiding the light slowly, squeezing it into a tiny little spot and guide it directly onto the high-speed photodetector that only have about 3 to 4 millimeter in diameter. That's our APD, avalanche photodetector. And yeah, those are the problems that we saw. Due to the interest of time, I go slightly quickly. And we use the same pool, the testing pool, so to test our ROV and also the communication and see how fast or how much can we push the technology by using the scintillating fiber. And this is actually a hobby paper. We try to use launch Skype in underwater environment. So if you be able to do Skype, it means that you have the technology is quite promising for bringing the internet in underwater ambient. Yep. We also try to send different wavelengths by using the scintillating fiber to detect different wavelengths so that be able to double, triple. And if you happen to have more wavelength, essentially being able to increase it substantially, just to mimic the technology that we use in the RF technology, the cell phone technology that's called MIMO. It's multiple input, multiple outputs type of technology that we try to mimic and try to do it in the optical domain in underwater. We make our fiber now. Chun Hong, that's my group member sitting there. He's the one who made the perovskite scintillating fiber. Same principle, same concept, but we put embedded all those very fast response nanoparticle in within the fiber so that be able to have the light conversions and very fast light conversion. It means that we'll be able to detect very high speed signal incidence towards the detector. Let me switch gear a little bit and then I'll join everything together. We now talk about the optical wireless comm, and I will talk about a technology that we develop in the lab, and then we try to merge these two together to extend the entire underwater comm to a more meaningful, say up to hundreds kilometers or so. That is the distributed optical fiber sensor that we developed. We developed this sensor for downhole sensing. That's together with the oil industry. And in downhole sensing, usually if they drill a well, oil well, they will drill a kilometers downwards, and then laterally can go up to 10 kilometers or so. But in the well, the wall of the well, they have an optical fiber. They either use different type of fiber called single mode fiber or multi-mode fiber for distributed temperature or acoustic sensing. But in our case, we built a system that being able to measure two. That is the acoustic vibration inside the well, down hole, up to about 10 kilometers or so, and temperature in every single meter. So that is special resolution that we'll be able to get. Yeah, of course, we put together this box and then have a lot of field trial. Actually, the box is being used by Ramco. Next week, we're going to Houston again for further evaluations of the new technology they developed for them. So we have two sensing points in a fiber that will be able to go up to, say, hundreds of kilometers. That is vibration, acoustic sound, and also the temperature sensing. So what is our vision? I only have 2 more slides to end. We hope to be able to integrate this technology by having the optical fiber pulling underwater, and every single 50 meters or so, we will branch out the signal, so that be able to integrate with the system that we built to control the equipment using the optical wireless comm. So wire because of fiber, wireless because of what we discussed about, by using light directly communicate with the device and our equipment. So that will be 2 applications. Fiber will be able to guide light. Light is energy. We also hope to be able to use this method to remotely charging or control, not only controlling, but charging the device that we put in underwater. We take some actions. In the canal, we already pull 1 kilometer of fiber doing this thing, but we do it in a very simple way by detecting some of the dolphin sound and whale sound that we pre-recorded and then play. Then with the human make sounds, for example, in the detecting sound from boats and etc. We also try to use the laser to send energy to certain devices. So I'm not sure whether we have published it. We always publish in very, very low impact factor journal, so it's free of charge after all. Maybe it's already published in Optics Express, that kind of paper. We enjoy doing so. And also, we currently have just pulled 50 meters just for a trial and to do the same thing. So in this case, we have more different type of fiber to address similar thing. That is quite close. If you happen to visit the monument, those are the place where we are pulling our fiber. And the next stage of development, we hope to be able to get to about 3 kilometers and then branch out every single 50 meters to do a lot of experiments. So this test bed is being able to establish eventually. There's huge lot of collaborations that we hope to be able to get it from the audience, and also a huge lot of work and open out many possibility for underwater comm. Actually, my very, very good team lead, Dr. Islam Asri, is sitting there, is watching that particular, and also the entire team and Chun Hong as well, Karen, etc. None of those were done by me, but by them. So I only here to present. Right, essentially, we hope to be able to do all those things. These are the systems that we put together: acoustic, temperature sensing, then communication, then together with the energy harvesting unit. Yeah, we wrote well, that's a very good review article, although it's slightly old now, by Tian Fengfei in Fudan University. He wrote a review on underwater optical wireless comm. And then in our case, we work on the commentary paper to talk about future. And if you're interested in this particular field, I encourage you to look up the two paper for further information. With this, I'll thank all for your attentions. And thank you. I stick to 25 minutes. I'm sorry.